All right, our next speaker is Gavin from Brown, and he's going to talk to us about an interactive debugger for Rust trait errors. Thank you, Gavin.
Thank you, Steve. So yes, today we will be talking about debugging trait errors in Rust, and I'm sure that many of you are not Rust developers, so I want to give you a sense of what it's like to be one. It's not important that you understand this code. What it is the simplest game possible made using Bevy, which is a game engine library for Rust, and there's a lot going on under the hood of this seemingly simple client code. If we look at the type signature for the add systems function, we see that the second parameter is required to implement into schedule configs, which is a trait. And for those of you who use the one true programming language, you would call this a type class, but today we're going to call them traits, so indulge me for a little bit. And we say that the parameter is bounded by the trait into schedule configs. Now, library authors are clever, and they use traits to check that parameters satisfy a specification. And I'm going to depict the problem with pictures so we don't have to look at any more really verbose Rust code. For a trait bound to type check, the compiler searches for a trait implementation proof. The tree in the background is what that search tree looks like, and the green path in the tree is the proof that this type has an implementation for the trait. I'll explain briefly the structure of this search tree. At the root, we have a trait bound, and beneath trait bounds are impl blocks. Again, for the Haskellites, those are class instances. And trait bounds and impl blocks are connected with dotted lines because they form an OR relationship. Only one impl block must be satisfied for the trait bound to be satisfied. Impl blocks may have themselves additional trait bounds, and these nodes are connected by solid lines because they form an AND relationship. That is, all children of an impl block must be satisfied for the impl block to be satisfied. This code does type check, but there's a common mistake that Bevy users make. They forget to write this type in their system parameters. This still looks like innocent code, however, the code no longer type checks. The search tree for this incorrect program does not find a proof. With this tree, it's not clear which one of those red X's is to blame for the error. Is it one of them, the one on the left, the one on the right? Is it both of them? And the problem gets even harder when I tell you that that's not the full search tree, this is the full search tree, and it has over 26,000 nodes. So that's a big problem. But a bigger problem for the user is that the trait inference process is a black box. Worse still is that the traits and impl blocks in this tree are all coming from the Bevy library. So you can't see them in your client code. The only information you get as the developer is that the type of your setup function does not implement the trait into schedule configs. To help us understand the problem at hand, let's walk through how the Rust compiler turns this proof search into a diagnostic. So with hundreds of failing obligations in the tree, which one should the compiler report? Well, the Rust compiler will take the least common ancestor of all these failures, which of course in this case is just the original trait bound, and it reports that as the root cause. The compiler reports where the error originated, including the line of code it came from, but furthermore, the compiler will add suggestions for types that do implement into schedule configs, which is these three circles in the tree. And this diagnostic is not all that helpful. And what I mean is that it doesn't facilitate localizing the actual error. The diagnostic only captures the top of the tree. All of the actual failing trait bounds, the nodes with the red X's, are below this circled region, and the compiler just threw them out. If the developer wants that information, they have to mentally recreate the proof search using documentation or source code. Now, we could do a handful of things to improve this diagnostic, and the Rust community is aware of this problem, so I want to tell you about the approach that they are taking. The Rust Foundation sponsored a community project to improve errors for trait-heavy crates. They looked at problems that real Rust developers had, they solicited for programs that exhibit bad error messages on Reddit, and the solution they landed on was this. Rust recently added a feature, similar to the Helium subset of Haskell, that allows library authors to annotate traits with domain-specific compiler messages. The main change to the diagnostic we built earlier is that the principal message now uses natural language. This is a domain-specific solution that requires action from library authors. So if the library you want to use doesn't have these annotations, well, you're out of luck and you're stuck with the generic messages. And these annotations do solve a problem, but not our problem. Our problem is that the information presented doesn't explain why setup isn't a valid system configuration. And explaining this why not question requires a non-trivial amount of context that isn't included in the diagnostic. For decades, we have relied on static textual diagnostics to communicate errors to developers. For simple programs with simple types, like this Fortran code from the 60s, this works great. But modern programming languages are not simple, and understanding an error may require more information than we would want to put in a textual diagnostic. Providing an interactive interface for an error allows us to include additional context without overwhelming the developer. What I am not advocating for is just using a GUI. People have tried to slap GUIs on similar problems in the past, and developers did the same, or sometimes they did even worse. So we can't just use a GUI. We need to be careful about how we design the interface and make sure that it's task-driven and well-crafted for the specific task. So now we'll get into the details of Argus, which is our interactive debugger for Rust trait errors. We'll talk about its design and how it fixes the limitations I've mentioned so far. The default interface shown is what we call the bottom-up interface. That means you are seeing the leaf nodes with the unsatisfied trait bounds. The bound currently shown in the interface on the left represents the pink highlighted node in the tree, and I'll mark it with that pink dot for us to remember what it is. Now, as I said before, there isn't just one failing leaf node, but there's a few hundred that are hidden behind this toggle. Each of these unsatisfied trait bounds represents one way to fix the program. If you take any one of these obligations and change the program such that the bound is now satisfied, a proof will be found. The developer has an intended program semantic in mind, and our problem is that we want to find a trait bound in this list that, when fixed, produces a program that matches their intent. The only thing we know about the user's intent is the program and the types they wrote. So our working assumption is that fewer changes to the code is probably better. And we developed a heuristic called inertia that estimates how intrusive the program change would be in order to satisfy a failing trait bound. And then we sort the full list of failing obligations by their inertia. As an example, consider the second bound in this list. If we wanted to satisfy this trait bound, then setup would need to be a function with 2 parameters instead of 1. The first is a mutable reference to the world, whatever that is, and the second one is an uninstantiated type variable that, when instantiated, better implements system param. Now, fixing that obligation is a lot of work, much more work than making the parameter to the function we already have with the correct arity implement system param. And even though we sort this list by inertia, it may not be obvious to the user which one they want to fix. Recall that the traits and implementation blocks in this tree are sort of implementation details of the Bevy library, not necessarily something the user is supposed to know about. So they might need additional context. And the context they would want is the provenance of the failing obligation. In other words, why does this bound need to be satisfied? As a reminder, in the interface, we're looking at the pink node in the tree, and as users incrementally unfold the tree, they traverse the tree from bottom upward. At the bottom of the interface, we're looking at the blue node in the tree, and by expanding the bottom-up interface, the user has the path from the pink node to the blue node, which represents the full provenance of this trait bound. Even further context is available if the user control-clicks on any symbol in the interface. We use the IDE jump to definition functionality to open up the source code for a type, trait, or implementation block. The bottom-up view facilitates localizing the root cause of a trait error, but it shows only the failing trait bounds. And sometimes the user may want the entire tree, including bounds that did succeed for maximal context. So we also provide the top-down interface, which is simply a window into the full search tree. The trait bound you see on the left is now the blue node in the tree, and as users explore the tree downward, they incrementally expand the children of each node. Here we see the 3 impl blocks for into schedule configs. And with enough exploration, the user can locate the unsatisfied bound at the leaf that we inspected in the bottom-up view. There's a lot of contextual information in the search tree, and we don't want to overwhelm the user with too much at once. This is why we decided to use incremental unfolding in the UI, but we also elide information by default. For example, where clauses and implementation blocks, type parameters, and some miscellaneous types like that of our setup function. All of these toggle on click when the user wishes to see the full information. The bottom-up and top-down interfaces provide complementary views of the information, and each has its own strengths and use cases. The big question still remains, does it actually help developers localize their trait errors, or did we make a cute interface with some nice icons? Well, of course, we ran a user study to find out. We recruited 25 participants of varied experience. For each task, we gave them a small program which was randomly selected from our pool of 7 tasks. 3 of these task programs use real-world libraries: Axum, a web framework, Bevy, the game engine we've seen today, and Diesel, a SQL query builder. 4 of the programs use synthetic libraries that we created just for this study. The Brew Crate provides a DSL for brewing potions, and the Space Crate provides a DSL for constructing intergalactic flight plans across some made-up universe. The synthetic crates allow us to test participants in domains we know are unfamiliar. But in order for the synthetic and the real-world tasks to be comparable, we designed the library such that the trait inference trees between the real-world and synthetic libraries are equivalent. Participants were instructed that the task program was from their coworker, and that they should explain to their coworker why the program didn't compile, and to provide a semantic preserving program fix that results in type-correct code. Participants had a maximum of 10 minutes per task, and we distinguish between time spent localizing an error and time spent fixing an error because our hypothesis is that Argus is more helpful in the localization process. With our running example program, a proper localization would be pointing out specifically the issue with the function parameter. For example, a successful localization from a participant came when they said, the parameters for setup are incorrect, mesh assets doesn't implement system param. Fixing this error would require participants to wrap the parameter in the resmute type we saw previously. We believe that Argus is less helpful in fixing errors because it requires knowledge of the library API, like the existence of the resmute type. And some of these real-world APIs are quite large. This is also difficult because resmute doesn't occur in the trait inference tree. Argus plays a few tricks to help people find these types, but it's not the tool's main focus. Participants engaged in 4 debugging tasks. They could use any tools, including LLMs and Google. In 2 of the tasks, they could additionally use Argus, and using Argus first or second was randomized. So how did our 25 participants do? This plot shows the localization rate, higher is better. The blue bar is participants who don't have Argus, and the yellow bar is participants who do have Argus. We observed that participants did significantly better when they had access to Argus. The next plot shows the time spent localizing an error. Here, lower is better. And again, we observe that participants localized significantly faster with Argus. And it's important that I point out the scary red line at the top of this plot. As a reminder, participants were cut off at 10 minutes. So for localization time without Argus, this really shows a lower bound. We don't know how long these participants would have taken if they had all day. As we hypothesized, participants localized significantly more errors and faster with Argus. Now let's look at how they did fixing their programs. For the fix rate, higher is better, and participants fixed a few more errors with Argus than without. And for the fix time, again, lower is better. Participants fixed programs a bit faster with Argus. Once again, note that 10-minute ceiling. So Argus significantly improved localization rate and time, and help developers fix their code. And this is great for the Rust community. But there are a lot of us who don't use Rust every day. But there are also a lot of search-based PL mechanisms in the world. Today, I talked about type class resolution, but there's also SMT-based tools, and there's even dynamic things like multi-method dispatch. I claim that all of these communities and more could benefit from an Argus-like interface. So if you work on a language with complex types or an involved runtime mechanism, you need an Argus-like panel. And fortunately, I've seen all your talks, so I know that there's plenty of you working in this area. I've gone through a lot today, so I'm happy to take your questions now.
Hello?
Hi.
Hi, this is Max from UC Berkeley. Thanks for this. Is a very interesting talk. I sort of see two things going on with the Argus tool here. There's the interface with the bottom-up, sort of top-down tree exploration, which is very neat. But then there's also this, you have to, as you said, there's a lot of X's that could potentially lead to a valid proof, and you sort them. And of course, in the example that you gave, the sorting does a very good job, right? It puts the thing that you actually wanted in the very first thing. So I'm wondering if you could say a little bit more about, to what degree is this inertia heuristic the secret sauce in these other domains that you're sort of, wanting to look into? Do you think a version of inertia could work, or are you imagining? I guess maybe even in your user study, did inertia always put the correct thing at the top, near the top? How much would that affect a user's, benefit from using your tool?
Yeah, so inertia is quite important in this case because, as you said, we have lots of information, and users probably aren't going to read through 100 lines just to try and find the one that they may or may not know is the one they want. In our user study, inertia does quite well, and we have details in the paper of how it compares to the Rust compiler heuristic as well as some other simpler heuristics we tried. For other domains, I don't know what the heuristic would be there. Someone would have to provide it, but I suspect that there is a inertia-like heuristic that we could use to try and help users out a little bit. Did I get all of your questions in there? Okay, thanks.
Hello, I'm Christine Riscala from the University of Melbourne, and yeah, thank you for your talk. I was curious about identifying bugs versus fixing bugs, and whether the same sort of information you think would be most helpful, that would be most helpful in one case would be most helpful for the other, or if we were to help people even more with fixing bugs, what's your intuition about?
Yeah, so I can show you the information we do provide for fixing bugs right now. So if you see, we have this is actually a different example, so bear with me for a second. There's a type that doesn't implement some trait, and so we can tell you the things that do implement that trait, which is very similar to what the compiler does. We can just do it for the more specific trait that you need. There are cases when this is kind of difficult. So one common pattern in Rust is the type state pattern, where depending on the type you have some methods available. And so we believe that fixing errors in the type state pattern probably requires some notion of that state machine that you have, and that users would want access to that. But it's an area we haven't quite explored. Thanks.
Good. Time for one last question.
Martin Maas, Google DeepMind. Thanks for the great talk. I really enjoyed this. I'm curious about comparison to AI and LLMs. So you mentioned in the user study, for example, that people had access to a chatbot, but I was wondering, if you build an AI-based tool around this and you give it all the code and you give it the error, do you have a good sense for how that would compare against your approach?
I have no idea. So I can tell you in the user study, people used all sorts of LLMs, online ones, local ones, chat-based, Copilot, whatever. They all did terribly, so nobody actually ever fixed or localized an error with an LLM. I would suspect that in order for this to actually work, you'd have to train the LLM on one specific library and your code and tell it exactly what you're trying to do. And sometimes these questions aren't, the developer might not know exactly what they're trying to do, so there's a little bit of fuzzy bits around the edge. But I suspected that an LLM-based approach would require a very specific LLM to one library.
Cool. Thanks.
Yeah.
All right, let's thank Gavin for a great talk.